let's start with continuity equation. Okay, let's apply the continuity equation for a turbulent flow. We'll just stick to Cartesian coordinates. So I know that my velocity field should satisfy this equation. So that means my UVW should satisfy this equation. I'm going to now split that velocity field into a mean and a fluctuating component. So I'm going to substitute U is equal to U mean plus U prime, V equal to V mean plus V prime, W is equal to W mean plus W prime, so that I can know whether I can deal with mean values. Del by del x of u plus u prime plus del by del y of v plus v prime plus del by del z of w plus w prime is equal to 0. I'll split that, dou u by dou x plus dou v by dou y plus dou w by dou z plus dou u prime by dou x plus dou v prime by dou y plus dou w prime by dou z is equal to, u bar, v bar, w bar, u bar, v bar, w bar. I have actually splitting it into mean and fluctuation. See, what I know is that the exact value satisfy the governing equation. Now I am substituting that exact value as mean plus fluctuation and just separated it out. Doubts? Yes. That is incompressible. The fluid flow can still be incompressible. What is that? You can have a density fluctuation. We are assuming that the flow is incompressible at the moment. In principle, you can have a density fluctuation also, though for most of the fluids, I mean, if you deal with gas, you will have to worry about, otherwise you won't have to worry about. So, a fluctuating velocity does not mean it's incompressible. Sorry, it is compressible. A fluctuating velocity does not mean it is compressible. Okay, you can have a compressible, you can have an incompressible turbulent flow, and that's what we are looking at. So maybe I should write down. Yeah, 1 second. Yeah. So when we dealt with continuity equation, right, we showed that. So what does it come out to be? D rho, no, del rho by del t plus divergence of rho u equal to 0. That's the full equation. So we could split this as del rho by del t plus u dot grad rho plus rho into divergence of u equal to 0. So that means d rho by dt plus rho into divergence of u is equal to 0. And we said if we are actually following a fluid element, and if the fluid element actually has a constant density, it will be an incompressible flow, because if d rho by dt equal to 0, then continuity equation is just divergence of u equal to 0. Okay, so this is an incompressible fluid, incompressible flow. Did we discuss this, incompressible flow versus incompressible fluid? Okay, so look, so what I have written on the right hand side is the continuity equation, right? So del rho by del t plus del dot rho u equal to 0. Now I am expanding the second term, which is divergence of the rho u, and I am assuming that rho is not a constant. Then what happens is that del rho by del t plus u dot grad rho plus rho into divergence of u is equal to 0. So that's just the product rule of differentiation, except that the differentiation is now a divergence. Okay, and if I combine the first two terms, I get a d rho by dt. What is d rho by dt? The substantial derivative of rho plus rho into divergence of u is equal to 0. What does substantial derivative indicate? following a fluid particle. Okay, so if I am following a fluid particle, okay, that's what d rho by dt says, that, and if I am seeing a change in the density of that fluid particle, then that is what d rho by dt will capture. But if I am following a fluid particle and if its density does not change, then d rho by dt is going to be 0. Okay, and so for a incompressible flow, so for an incompressible flow, d rho by dt is 0, and therefore the continuity equation is just divergence of u is equal to 0. But if you want to talk about an incompressible fluid, then you would simply say rho is a constant. Okay, but either way you are going to get divergence of u is equal to 0. Anyway, that's not important if you didn't really follow. The point is that divergence of u is equal to 0 is for incompressible fluid and incompressible flow. Okay, so we are dealing with continuity. We have written down in the Cartesian coordinates and we have split it into mean values and the fluctuations. Okay, now what we are going to do is we are going to integrate this equation. Okay, this entire equation we will integrate from 0 to t dt. I am allowed to do that, okay, where t is some time that I have taken, so that I can average out during that time, and therefore all the fluctuations, therefore, you know, whatever comes out I can put to 0. So that's the idea. So if I do that, and then I can do a 1 by t, of course. So the first term, okay, dou u bar by dou x, is that function of time? No. So I can just do the integration. Okay, so it basically gives you dou u bar by dou x. That's actually a constant as far as integration is concerned. Next term is also a constant. Next term is also a constant, plus u prime. U prime is definitely a function of time, but I interchange my integration and differentiation. I will first do the integration and then do the differentiation. So I will write this as rather del by del x of integral 0 to t u prime dt plus del by del y of integral 0 to t v prime dt plus del by del z of integral 0 to t w prime dt is equal to 0. And you do know that this is 0, that's 0, that's 0, and therefore you basically get back that dou u bar by dou x plus dou v bar by dou y plus dou w bar by dou z is equal to 0. In other words, the mean velocity satisfies continuity equation. That's what you have proven. Okay, so if you want to only calculate a mean value of velocity, you can still use the same continuity equation without any change. That's clear, right? So let's worry about what is momentum conservation equation going to do. Okay, so we'll just write down again x momentum and we'll just deal with that. So that's my x component of momentum conservation, and I'm going to substitute u equal to u bar plus u prime plus, now in some of the next terms, so if you substitute u bar plus u prime into del by del x of u bar plus u prime plus the next term is v bar plus v prime times del by del y of u bar plus u prime plus w bar plus w prime times del by del z of u bar plus u prime is equal to minus del by del x of p bar plus p prime plus del square of u bar plus u prime. That's what, if I simply substitute u is equal to u prime. Okay. And what happens if we expand? Rho first term dou u bar by dou t plus dou u prime by dou t plus, there are 4 terms that are going to come up now, right? Because it's u bar plus u prime times del by del x of u bar plus u times. So, u bar del u bar by del x plus u bar del u prime by del x plus u prime del u bar by del x plus u prime del u prime by del x. That's first the 4 terms, and then there will be 4 more terms from the next expression, v bar dou u bar by dou y plus v bar dou u prime by dou y plus v prime dou v bar by dou u bar by dou y plus v prime dou u prime by dou y plus, so should I draw things? So this is that, this is that, next is, oh sorry, I did a mistake. So that is that, this is that, last term, w bar dou u bar by dou y dou z plus w prime dou u bar by u prime by dou z plus w prime dou u prime by dou z. I'm just expanding, okay. Did I miss something in the equation, this equation? Some important fluid property? Viscosity, huh? This is mu. Just simple expansion, okay. What is the next step we should do? Integrate, okay. Integrate this expression from 0 to t and throw away all the unnecessary terms that we have. So we, this entire expression, okay, integrated from 0 to t dt. So that's what we are doing. So all the terms that have just u prime, okay, just one fluctuating variable will go away when we do this integration, right? But there, if there are any products that are going to stay there, just the way that happened for the continuity equation, right? For continuity equation, we had seen that we could interchange the order of differentiation and integration, and therefore all the terms that were there as just primes left, you know, it was gone. But then if there was a u prime square or a u prime v prime, all of them are going to stay back. So therefore I can throw away all the unnecessary terms that we have written down now, which would include that, 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 this, this, and that. So the moment I do the integration, all of them will go away, and therefore what I have, left out is rho times dou u bar by dou t plus u bar dou u bar by dou x plus v bar dou u bar by dou y plus w bar dou u bar by dou z is equal to minus dou p bar by dou x plus mu del square u bar minus integral 0 to t u prime dou u prime by dou x multiplied by rho plus rho integral 0 to t v prime dou u prime by dou y plus rho integral 0 to t w prime dou u prime by dou z. That's what we end up with. So, some of the terms stayed back, right? All the terms which had two primed variables, okay, which were the products of the fluctuations, they will not go away during the integration, they will stay. Okay. So, what you are seeing is that the left hand side is exactly like what we had for our the exact solution. All the terms that had these double primes, I have moved to right hand side for convenience and written down, and you see that if you compare with the full expression that we had, this is what we used to have, but now this has come out to be extra, okay, which are basically some integrals which we of course do not know. Or another way of saying it is that the mean velocity does not satisfy the x momentum equation. Okay, if you want to write down the x momentum equation for the mean velocity along with the terms that you originally had, there are going to be additional contributions. Those additional contributions are in terms of fluctuating velocities, or rather products of fluctuating velocities. But those are the products of fluctuating velocities that we are really looking for. We do not know what it is. So, we actually try to get that down, okay, remove that, but we could not remove it, okay, they won't go away, they will remain there. And that is basically the main issue with turbulent flow. So, the whole problem comes out is, can we get rid of them, or can we use some other fact, okay, to remove that and therefore able to solve the equation. Is that clear? So, this will happen for any y momentum is z momentum, all the equations. That's clear? Okay. So, basically you are now convinced that it's not a simple problem to solve. Okay. So, therefore, we actually need to do some alternate ways of dealing with these equations, which we'll see in the next class. Any questions? Yeah. There is a dt, yes.